And if I recall correctly, what we now want to do next is to implement our join and append functions to our string class. And since the join function will basically just call append a couple of times on the vector of strings which we have passed to it, it would be good to start with the append function. So I would suggest that Mr. Leonardo would try to implement set function. Is it working? Or do you have issues to connect? Okay.
Type the name wrong. What's the name of the program again? To connect?
VNC Viewer. You might also download it as Ultra VNC.
Just kick me out. See, I'm just trying to connect, but it's just kicking me out of the program. One moment.
What error are you getting?
It just timed out.
Okay. Wait, let's check whether it's actually still working. Maybe there is something not configured properly. It is possible that the IP changed. Yes, it did. Okay, now it should work.
Is it the same as last time?
Yes.
Contact. Oh, there you go. Now it prompted me to put in the password. All right. So, pending. So, would I be able to just update the data structure with the new length and size, and use a STL append function on the pdata?
No, that will not work because pdata is a raw pointer, so we will need to allocate new memory
Okay.
for that. There are two ways how you can implement it. One is that you just allocate a new object for pdata and then replace it, and the other option would be that you create a whole new m object with which basically just contains pdata plus length
Plus
and size, which probably will be the more elegant approach.
Okay.
Although then we will need to take a look how to dispose of the old m, since usually we use this release, which we in this case would not want. No, we can use it. So the approach would be this: you create an m object, you copy the data from the old m object to the new one, then you can call release, and then you would assign the currently newly created m object to the member of this object, so that it then takes place of the old m.
Makes sense. And here, would I be able to just use a long string to save the previous content of the or wide string to save the previous content of the
What do you mean long string? You mean a string from the STL?
yeah.
Or that's not what's intended. Intended is to kind of not need the STL. In a later part of the lecture, we'll replace the std vector, which we used above, with our own structure, either a list or a vector. But the idea is that we can create own container objects which do not require the STL. So, I mean, for start, you still can use the data from the old m object. So we just create a new m variable with a different name, like m underscore new or something like that, and then you can copy all the data to it, and then once you're done with it, then you can release the old object and replace it with the newly created one.
So I guess your length plus your length was in size T, right?
Um,
Okay.
and why are you adding one more element to the array and only one?
Shouldn't it be only the size that we're creating, shouldn't it be the U length of the original plus only one character? Or are we
We are appending a whole string.
okay? So it should be
It should be the length from the other string.
the length. Okay. So then also this. So already have a new. Would it work to just put a plus here with the?
Now you will need to
Hmm.
copy first the data from the old m, and
Mm.
then to the right offset, copy the data of the m from the other string. So we'll need two memcopy operations, one going directly
Mm.
to MNUP data, and the other one going to MNUP data plus the length of the old array.
Sorry, I'm not familiar with memcopy. Where do I add the offset? Is it at the end?
No, you just can you can just mathematically add to pdata.
Oh, okay.
At the in the first argument, you can just write an m new pdata plus m u length, not other.
Yeah,
You want the
the
current
extent.
one. Mm-hmm.
Okay. Uh, I guess we can use the release.
Mm-hmm.
Do I have to recreate the M, or does the release not
You
destroy
have
it?
m has destroyed. So release has
Okay.
destroyed m, and then you can just assign m new to m. Mm-hmm.
think
Okay. Well,
should be it.
well, almost one thing we are missing is to null terminate the array. So I think if you look into create, we always create at least one more character, so that we can put a terminating null always at the end of the string, such that we can then use the string directly for functions that take a normal C-style string. Yeah.
Yeah, like so.
The other dot should go because we want the length, which is the sum of both strings, which is our now new
yeah, right.
length. Okay, now we need the test case.
I could use the same string, but
And now we can print it maybe, or yeah, we can also inspect the breakpoint.
Oh.
Okay, there is a bug somewhere. Just click no, and then you can click on any of the bugs and it will bring you to... you need to define the variable first, so you need to specify which type mu will have.
Okay. For the mu, right.
I guess if you look in the create function, you will see what type it returns.
String and crazy. I think that's it.
Almost. The end character should go, because we cannot assign to a reference a return value.
Okay.
Yeah, now it should compile. Wait. Almost. It should have an asterisk because we have pointers.
Oh.
Also, the type is SX string, not CX string. Capital S at the beginning and an asterisk.
This or
At the beginning of the line, a capital S. SX string. And the asterisk should be there where it was.
Okay.
Yeah. Okay.
Should be test append 1. Data test 1,
Yep,
test 2.
it
Yes.
works.
Okay.
Great.
Good.
Next assignment, the join function.
Just 1 second, someone's knocking at the door. I'll be right back.
Mm-hmm.
Sorry about that.
Problem.
So join. So vector of strings. Okay. Right here. Don't remember if the length is in STL.
Yeah, size.
Then can put I think this should work.
Yeah, it does not behave exactly as we want, so it will always leave a separator at the end. The idea is that
Okay,
the join
right.
function will only leave a separator in between the strings, but not append one to the last string added.
Yeah, that makes sense. Could do something not as pretty. By doing this and then just have one list.
That will fail spectacularly in two ways.
Oh.
Well, first of all, if you have size, so if assuming you have size 0, then the first loop
Correct.
will evaluate to -1, but since it's unsigned, so it will be max value, so it will be 4 billion. So the I will iterate until 4 billion, so that's not good. And the next issue is that even if that would have worked, if the string is empty and you try to get string from 0, it will create a crash.
Okay, that makes sense.
Usually an easy way around is to just move the separator one line up and then check if I is greater than 0. So if I greater 0, then first add separator, and that's it.
So the test case. Oh. String. always forget how to create vectors in C++.
So without any special tricks, the simplest way is just to create an empty vector and then to use the pushback function to attach, to add new elements to it a couple times. No, that you don't need the namespace again. If you already have an object, it will automatically pick the right namespace for you. You need to specify an argument.
Okay, that's what's okay. All right. Okay.
And we should save the return value to something, otherwise it will be
Okay.
not interesting. Also, if I recall correctly, we have defined the join function as a static one, so it could be called directly on, so without an object. Once you're done with the test case, I can show you how to do that.
Okay, yeah. So just this, and then return to something.
Well, you need to specify the class it belongs to. So cx string pointy bracket char double point. Just can use the type you want as a namespace, so to say. Yeah.
Okay.
And then of course assign the returning value to some new variable. Yep.
Okay.
Let's run it.
Oops.
May I take the mouse for a second?
Yep.
Oh, I think I know what m doesn't exist. Yeah. If you are appending to an empty string, in an empty string there is no m.
Yeah. Okay.
So
you should check if there's m.
Yes. Well, you can check if there is an m, and if there is no m, then just use the assign function to assign to the current string and then return. So it would be just a few lines on top of the append without changing the rest of the append. That would be a reasonably easy workaround.
This works for null pointers, right?
Yeah.
Then they just create m as empty?
You can use just asterisk this is equals other semicolon and then return semicolon.
Sorry, asterisk this
is equals other semicolon and return in the next line and then semicolon again. Also, what would be good to add is to check if other is null. So you could add another if before the current if and check if other.m is empty, then return. Although I think we already do this in the... No, we don't. That would be a good check, because otherwise, if you try to append an empty string, then you would also get a crash.
Okay.
I would do it first. Because if there is nothing to do, then there is nothing to do. That's the hope. Let's run it. Okay.
And test.
Yep.
Data.
Wait.
It's missing one test.
It's missing one test, yes.
Oh, it's because I forgot to.
Yes.
This. Yep,
Perfect.
works.
Good, very good. So, I think, if I'm correct, then we don't really have anything else to add to our string, except of course all the homework assignments, which will need to be done in your spare time. So I would say we will try to create a new container type to replace the vector which we were using here. So it would be nice if our example at the end does not need anything from the STL. So then I will create a new header, header file, and you can either call it list or x vector or x array. That would be up to us. They depend on the exact same. They are mostly the same. They're just different details. So, for example, in STL, the list cannot be addressed by index, and if I recall correctly, the array is just you cannot grow the arrays. You can only grow vectors. And the question would be how we would like to implement our particular element. I think I would call it a list, since a list is like it does not implies anything about the memory layout, and a list can have access by index. For example, the Qt list implementation allows to access by index, and it's not something that one would normally associate with a list, that it can only be iterated from front to back or back to front, but wouldn't be accessible by index. So let's call it xlist, and then we'll think about which functionality we'll add to it. Xlist h.
Should I disconnect?
Yes. Okay, so template type name team and class cxlist. Let's quickly take a look here. Our string, right? That was not. Then one more thing I want. That's right. So let's continue with the list. So we of course need some constructor for it, and some destructor would also be good to have. We might not need it, but let's see. Probably will need it. And if we would be creating some object which we would like in future to derive something from, then it would be good to always make the destructor virtual. But in case of lists, it's rather not expected that you would extend the list with anything special, so we don't need to do that. And it's a very small but yet present performance increase in not having a virtual function, but it's extremely minimal difference nowadays. With very old systems that were very slow, that of course was relatively more significant, but nowadays it just adds about one more instruction to the machine code, to the call, if you have a virtual function, which is basically negligible. Okay, and now let's see what functions will we need for our list. Well, an append function, of course, which takes a const t reference item. Then we would like to have some remove function, maybe, so that we can remove an element. And since We could do it in three ways. First of all, we could try to remove an element by an internal pointer that we first have to obtain from the list. The other option would be to have some iterators like STL does it, which would keep some internal reference and allow us to do this operation. And the third option would be to do it by index, which would mean, of course, that we would need to have indices in our list from the very start. But I think since we are using it here, we want to use it here for the split function. Usually when passing things, with the split function here somewhere, when passing things, it is usually good to be able to access elements by index. So we will make our list from the get-go support indices. And then we have to quickly think about how to do that. So since we have the ability to access something at index, we'd also want the ability to access the index. Doesn't need to be const. We should have two functions, I guess. Const t reference at index. Let's call it index. Index comma const and a non-const. Oops. Non-const version, which is not const. Alright, and we need to provide function bodies for everything, since this will be a template such that we can store anything we want. Append has return type of void. Boolean remove could have a boolean indicating whether it successfully removed an element. Basically, it will return false if the index is out of the bounds. And of course, these two will return an element by reference from the list. So, well, for now it's kind of not elegant to return anything. So, if we cannot return something currently in a reasonable way, and returning references, of course, it doesn't really work to return a reference if you not have an object that would store the thing to which you return the reference. But what we can do for the compiler not to complain that there is no return value, we can just throw an exception, because the compiler then knows that there will be no return, so it's fine. And since it's not implemented, it will then just throw us an exception reminding us to implement it. So we have our append, remove, add, another add. We should also add a prepend, so kind of like insert at the top. This is also quite useful to have. And then there is like a huge myriad of other useful functions which we might add, like first, last, take, first. Take first is like take plus remove. Take last. Sorry, first plus remove, and last plus remove. We could kind of treat it like strings, having some options to get sublists. So mid int e on int count, and then we also could have like left and right, like with the string, so that we can get something from one of the ends of the string, or in this case from one of the ends of the list. It would be good also to have some sort of find function, although finding would mean that we can somehow compare the element. So we could also say that we do not implement any find function. If someone wants to search for something in their list, they need to implement their own find function, which does that, just going from the beginning till the end. Or alternatively, what we could also do is we could implement a find function which instead of taking a value to search for, would rather take a function which would a function pointer which would then take a reference to the current element and return true or false on the match. That might be useful, so let's add this as well. Int find, then we would have a bool match, which then takes a const the item and returns a value. We could add a int start index, and we also could specify a parameter to pass to the find function. Oops. Which is quite useful in many cases, so we will just add it here to have it just in case. And one more thing that we perhaps should add, where should we? We could extend this remove function such that we can specify a count. So if we want to remove more than one element, such that we can remove multiple elements from the list at a starting offset. So this actually haven't seen this particular way of doing things implemented in Qt by index, I think. But if you are using STL, you can use remove arrays. They call it the remove arrays, and then you can specify a start and end iterator. So they will then really remove our range. In our case, since we want to do everything by index, we will do it this way. And we have our find function. We could have also a reverse find. Why not? I forgot the semicolon. I think I can stop that. So find, but then the starting index would be -1. And of course we need some return value or a throw so that the compiler does not complain. Yes, I think that's the basics of what our class has to be able to do. So let's look at how we will store the data internally. So since we want to be able to access things by index, it would be necessary to somehow have an array which will point to which will hold the individual elements of the list. And at this point we would not need to make the list linked in any way, since we can easily access any element by its index. So I think we'll just do it this way, and we will also keep everything in a member sub-object. That is quite useful if we would later want to make it something copy on write or something like that. So we have here our list, we have our struct element, and this will be just our m, which by default is null. It will need to be filled with something, and then it will contain well, an array. So t asterisk data, t array data. The array size is not yet defined, so we will be able to change it, and we should also have a well, either a size or an int. On string use size, so we should also use size 10. A variable count or size. Let's say size, and the other one will be capacity. The idea is that we can create an array which is larger than the amount of elements that we want to store, such that we don't need to recreate this array each time we want to change something about the list. So when we are appending elements to the back, of course when we are appending at the front, that will be more computationally intensive. We could try to optimize this actually by having like a buffer, so our a data, and then have a pointer that points somewhere in the middle, and such that we can kind of append on both ends and then just adjust individual pointers. But I think for the start we should not overcomplicate things, and also it's not too much of a expensive operation to just move everything in a list if the list is not too big yet. So I think this will be good enough, and since we said we'll be using size t, we should change our indices all to be size t in nature. That will be more in line with modern coding standards. Right, so we have our element. We could kind of try to optimize this by doing it like this. So what this gives us is an array, so that we can have one single memory block, which will hold our variables plus our array. And this is, I think, a small improvement, since we then only need one memory allocation operation instead of two. Yeah. And as long as we don't have any other arrays of undefined length, this works perfectly fine. It kind of is only then a bit of a problem if we would need like the ability to have multiple elements of an arbitrary size. So in which case we just go with allocating either allocating the memory still in one block and then just setting the pointers to the right value, or just allocating multiple memory blocks. Okay. So of course the first thing that we need to implement is the append, but we also should look into create. Oh right, we forgot one more function which is quite useful to have. It will be a get size, so that we know how many elements there are. M size null. Okay. So this will return us the current size, and then we'll start with implementing append. We only have one way to add things, well, append or prepend, so we should probably generate a create function again here that will allow us to create an M, such that we can, like with a string, easily create new M's when needed. Create int, sorry, size t, new capacity, and M is equals malloc size of s x list. Right, we need to improve that. Right, we want to store pointers, so there should be an array of pointers to the data object, since we want to be able to delete them individually and are not creating a vector-like structure where everything would be in memory in one consecutive memory block. The way we want this to work is to for the array to hold actual pointers to the elements. So we have malloc size x list plus size of testern times new capacity. We could also just write size of void asterisk, because a pointer is always a pointer and always has the same size. But for now, let's leave it like this, and then we will set size, of course, to 0, because there is nothing in the new M, capacity to new capacity, and we can return new M. One thing we could, by the way, change here, since we are using malloc, is we can use the realloc function to try to change the size of a memory area without always creating a new allocation. So the way it works is, since it knows that we want just to extend the memory block, if there is a free address space after the currently used memory, then it will just allocate memory to the right address, and then you don't need to copy the content of your existing memory. So this maybe is something we could improve. So we could create a function called grow, as that will be a void, since it doesn't take anything. Grow will again take new capacity. We need to check if an M already exists, or rather if an M does not exist. So if an M does not exist, then we just to an m, and before that m is equals create new capacity. But if an m exists, then we will try to m p data, a data ist gleich why is it not so? No, was it 1L? Well, okay. IntelliSense is broken. I'm pretty sure it's with 2L. malloc is also with 2L. So now we just there was another thing to check. This is fine, but we should of course check if this thing, so if capacity is greater or equal new capacity, then we don't do anything. And of course, if we did the realloc, then we can just assign, just extend the capacity to the new size. Okay, right. So let's go and call it expand new capacity. That sounds better. And we of course need some release. Also, we forgot like assignment and other operators here, but this is something that a list that can be added later. That is not so well. It will be needed for our use case, but it's something we can do later. But here we should also add a release function as well. So release if m, then free m and m is equals null. But what we also will need to do, well, that will depend on how we want to operate. So what we want is to delete all the elements we have created for the list, so all the list entries. And the idea of the release function would be that we would call this to release m, but we could either have a second function clear, which would erase all the elements in the list, or we could have make it part of the release function. Which one is more elegant? I guess we will make release to the releasing. So here we add a to do it will have to be done later. So for now here we just add release to our destructor. We have already our size function, we have our append. So let's try with doing append, with appending something. So well, expand to size plus 1. So we ensure we have enough room to add something, and then we can just find the next free spot. So m a from m size plus plus is equals, and this will need to be a new element. So new t. If we want to assign, to use the copy constructor, assign the value of the element that was passed to us. There is a improvement that can be done later, being that if size of t is less than the size of a pointer, that we then don't use this array as a array of pointers, but rather as an array of values. So we can add here a to do if size of t is less than, well, less or equals size of t asterisk this is quite a useful improvement, because often you make a list of pointers or a list of integers or doubles or booleans or something, and then creating a whole memory allocation each time is excessive and not really needed. Right, so we expand. We could have here a test that validates that the expansion worked successfully, but I think we don't need that. Also, I was thinking about one more function that would be nice to have, would be a so-called insert function. And the idea of an insert is that you can specify an index where you want something to go, and then it will be inserted at this position, and the things after that will be shifted by 1. We could have also an insert function that takes another list and inserts a list of sub-elements. So that will be funny as well. And then we of course want our get functions. So right, and the next thing we also need to decide is how do we want to treat situations where someone tries to access something with the add function at an index which does not exist. Since we are returning references, we cannot really return an error, but what we can do is we can throw an error. And thinking about this, we could make the insert function and the remove function maybe not return values, but also throw errors if someone tries to access an invalid index. I think this would be an improvement, since we want to be consistent with the way our object works. So we don't want like some of the functions having a return value while other of the functions will be throwing exceptions. So it is reasonable to just throw exceptions always whenever an invalid index is being accessed. So you could create a helper function for that. Ball test index not int size the index. I think we used capital I for indices, if I recall correctly. And if m, so if there is no m, or m size is less or equals index, then return false. Else return true. Although technically you could also say that remove will be successful if we try to remove something that is not in the list already. But I guess this is convenient, but it's also like not fail-safe. Ideally, we should really ensure that we always check the indices, even if it would kind of work even if we don't use small I. So I will change this here to capital I. I'd rather have the capital I's everywhere. Count. Right, so we test index, and if it fails, then throw we could later create an own exception type, but for now let's just throw strings with an error. And else, if we want to, we wanted first to implement the add function. So let's start with this. So data add index, and since we need to do it like this, and we will need to change this again if we want this optimization.
What's the difference here between the constant function and the non-constant function?
There kind of will not be any. The only difference is the return value. So if we get a const t, we can read it, but we cannot modify it, at least not without casting. And with this function, we can get it and we can modify it. So we can write list.add 3, for example, is equals, and then assign something to it at this place, which is quite nice. But if we would, for example, have a const list, then this function would not be accessible. So we need the const version of the function, which basing on our definition, will only also allow just read access to the element and not allow you to change it. This of course can be bypassed if you cast this then to something else, but that's kind of the story of every const thing in C++. So this will be fine. Okay, so cx list from cx string from char my list append test1, test2, test3. Since we have a constructor that takes a character for our cx string, we can directly write it like this. We don't need to write cx string. We don't need to waste time typing things like this. The compiler automatically finds the right constructor for us. Right, so let's run it. Okay, we have some error somewhere. Right, we changed it's capital I. Expand. Alright, expand just returns. It does not return anything. Right, and for realloc we need to specify the old memory block. I forgot about that. So as you see, it takes the old memory area, then the new size, and then it will give you a new pointer to a memory block which contains the data from the old memory block, but is bigger at the size that we have specified. And it can, in the way the function is defined, is it can give you a new pointer, but it can also give you the old pointer. If it was able to reserve more memory, more consecutive memory at the given starting address, then it will not change the return value, and then it does not need to copy anything. So as mentioned, this is the optimization. What are we missing? All right. We have to reallocate the whole M thing, of course, not just the data, since this is not a separate memory block. We have one that covers everything. Now it should compile. Still it doesn't. Right, it wants a cast to the new type, so actually it should complain about there being no cast also here. So let's add it there just in case. The thing with templates is that they kind of are evaluated as it goes, so it very rarely throws you all the errors that it will encounter at one go. Instead, usually it just gives you some errors and gives you some more errors, and so on and so on. I pressed F5 once too much, so let's can try. So we have our list, which have size and capacity set to 3, and then our data which we cannot yet access. So we could add here a test case for size I is equal 0, I is less than my list. Oops, that's another typo. I wanted the L to be capital. My list dot get size, comma I plus plus, and here printf %s backslash n, comma my list punkt add I punkt c string and small t. Well, it kind of worked. We should probably just add a few more new lines here so that we know where the old test cases ended. this one. Yep, this one test2 test3. So the very basic functionality of our list already works. I think what would be good would be to add the optimization right now, because if we start adding other things and then don't think about the optimization, we'll probably forget to add it in all the cases. So let's do this now, and as said, it's quite a significant optimization. And we are still missing a mechanism to remove all the elements, so we will need to add this as well. So as mentioned, we will just use an if like this first. If size t is less than or less or equals size of this, then we need to cast the array entry to the reference of the array entry to t asterisk, and then dereference this and assign it with that. Right, and since we are here in this if only comparing things which are known during the compile time, effectively this if and this branching will not be part of the compiled code. The code will either contain this line or that line, and that will be decided by the compiler during the compile time. So it is really a very well-performing optimization. Okay, and here of course the other situation is and we just copy this part at index, and then we want to dereference. So we dereference this, so we get a reference on this address, we turn it to this, and then we, yeah, that should be right. And the table can be removed. Okay, right. So we have this, we have this. We have not forgot anything yet. So let's redo our test case just with integers. By list I. One, two, three, my list I. My list I at E. We don't need this, and here we % D. So let's quickly check if this works as well. We created a crash somewhere, not good. Why did we release M? We broke something. Let's see. If size t is less than the pointer, that should be fine. Let's quickly add some breakpoints just to see whether we access those things at the right situations. Okay. That is not what we wanted. This should not. Oh. As it happens, our string, since it only contains one member variable, which is one pointer, here this M, has also the size of 8, or in case of 32-bit of 4 bytes. in which case it was in the first case here. So for this to work correctly, we need to improve on that. So we have here the memory of the type. So we need first to execute new on it. So new. What's the syntax for that? I don't remember. There is a syntax how to call new on a existing memory block. Let me quickly check that. Then we'll use it. If I recall correctly, it was not really so super intuitive. Right. So if this is right, then then what we would need to do would be new from the memory block and then the type. So T. Yeah, this is definitely not a very intuitive thing. Right, and we will need to think about doing this correctly every time. This will also make our cleanup a little bit more complicated. Okay, well, not quite. Still crashing. Does this return a different... It should not return a different value as such. What asterisk ptr is equals... Okay, we'll quickly need to debug that. Oops. How to make this optimization work best. So ptr and t asterisk test is equals t right breakpoint run. Okay, so pointer has a certain value, test has the same numerical value, which is correct. So now if we access this, so we cast it to an asterisk, the reference, and then we dereference this, that should be right. But there it's DDD, so we have something. And also this does not have the right offset, it has 408. While here it had the... Oh, I see the problem, let's just increment let's just increment this separately, then it should be fine. Okay, so again we have our memory, both objects have the same value. Then if we enter here, this still has the right value, so now m should be null, right? Then it will want to create an m, which should be fine as well. Then we do the copying, and then we return this. Right, now it works. Continue. Right, this one should be fine. And wrong window again, and voila, it worked. So if we go back here. We in principle don't need the test case. We just need this to be there, and that's it. Right, we could improve on that as well, could we? Yes. We don't need to use the sum, we could just use the constructor directly, then it will assign the new, and then we could make plus plus here again, then it's a one-liner. Let's run it. Yep, didn't crash, nice. So now what we also need to do is to take care of the cleanup properly. So the idea would be wrong file, that in our release we will just see well, how many elements there are still in the list, and if there are any, then we will remove them one by one, and if there are none, then we don't have anything to do. So for so if we want to release the M without deleting elements, we just first have to set M size to 0, and that's it. So this is reasonably easy. And now here we will again have this optimization being used. Right, so the easy case is of course just delete the pointer, and if I recall correctly, if we have something here as an object, we need to call the delete operator on it, but only if it has a delete, only if it has a delete operator. Because we don't want to call like we don't want to assume that there is a delete operator, because there might not be. I'm thinking how to do that best. If we knew that the thing is not a class, then what we could do is just call 3 on it, but this is not what we want. One moment, please. I have to review how remember how this was done properly. So if these are simple elements which don't need any operation, then we just would not need this first case here. But since this can be an object on which we first called the constructor, then we might need to delete it. Just that the thing is that normally delete will free the memory, and we don't want to free the memory. Should have prepared that up front, I guess, but Right. Operator delete and then the memory address we want to free. That should be the way to do it. Let's see if it works. As you see, it is quite not very intuitive, so it's easy to forget if one didn't use this for some time. So let's try both cases here, whether they work as expected. And as soon as we exit the scope here, we will call our release. So let's run it. Okay, it is complaining about something. Alright, that was to be expected, of course. Right, so this is the first case where we delete the more complex structure. So when we enter here, we should enter our something. Great. I don't want to go through everything, so let's just add a breakpoint on our delete here. Now release here. We should arrive at it. No, we did not. That should be the right pointer to the object. I will debug that and we will continue with this during the next lecture. I did such things long time ago, but I just don't remember how to properly free that if we don't know the difference whether it's a complex object or a machine type. Because apparently it tried to free the memory in the end, not just invoke the delete operator on it. So that's why it's now crashing. Yeah, I will debug that and we will have a working version next time. Then we will continue with adding a I'll write some notes down. We will add a copy constructor and a assignment operator. And we could then add optionally some more operators, but this will be this is not necessary. So usually you could have like plus equals that will just shortcut to append, and you could use the left shift operator to also kind of append elements, so they are just in a slightly different way. So the shift operator would not would have a return value which would be the same object as was passed in, such that you can concatenate multiple of these operators in order to in order to append multiple elements into the list. Yeah, but that we will do during the next lecture, and so there will not be no homework for now. I think you have still enough to do with the string homework. And during the next lecture we will implement some of the functions during the lecture, and some of them will be then left for homework assignments. So yeah, that's that for today. Have a nice end of the week. Bye bye.
Thank you. Bye bye.